Okay, good morning. We will start today's seminar. There will be two persons, Dr. Jacqueline Suzett Rechy Garcia, and from in-house, from IAA, Dr. Martin Guerrero. They will talk about the orientation of the collimated outflow of planetary nebula, the Independence Day. Martin is from IAA. He started here with a Ramon y Cajal fellowship in 2003. Then he promoted to científico titular in 2006, and then again promoted to investigador científico in 2010. And Martin will be the person who introduced Jacqueline. Thank you.
Okay, thank you very much. Jacqueline Suzett Rechy Garcia, also known as Jackie. She's got her licenciatura in Universidad Veracruzana in 2011. Okay, then she moved to UNAM in Mexico City, where she's got his maestria in 2014. And then she started her PhD under the supervision of Dr. Miriam Peña from the Instituto de Astronomía, and Pablo Velázquez from Nucleares, Instituto de Ciencias Nucleares. And she got her PhD working on a peculiar kind of planetary nebula that actually she discovered, or she named, that are those that they have bipolar, that have collimated outflows that you only see through spectroscopic observation. Those are the spectroscopic bipolar nebula that she called. She's got her PhD last year in July. From then she's got the Premio Paris Business to the best PhD in the Instituto de Astronomía, and she's been also named for Alfonso Caso PhD prize at the Ciudad de Mexico. So this talk, we are going to be talking together. I'm going to start, and Jackie will follow, and we will changing each other like Pimpinela, as Isabel reminds us very kindly. Okay, so I'm going to start. This is a project that I thought long time ago about the orientation of collimated outflows in planetary nebula, and how we would be able to determine the real speed of those outflows, which is something that we cannot say from the observation of one single outflow. And we think we have found the way to fix this problem, so we are somehow independent of the orientation of the outflow. So we call this the Independence Day, and actually the talk was intended to be given here on July the 4th, and so we prepared this. But then Jackie has the opportunity to go to Tenerife for a meeting, and then we have to postpone this, so this is not going to be on July the 4th, but today is the Día de la Independencia de Argentina. So we are here celebrating the Independence Day of Argentina. Okay, so let's start. We're going to be talking about collimated outflows in planetary nebulae, the statistical approach that we have applied here, how we have selected the sample, what are the parameters that we are going to be investigating here, and possible biases in the data sample selection and data study. Then I'm going to present you some preliminary results. Jackie made a close examination of those data with some very particular examples, and finally the interpretation that we give to our results. So what is a collimated outflow? Well, many or significant fraction of PN, they exhibit fast collimated outflows. Those are features that we see in kinematical observation, that they have expansion velocities that they are very different from those of the nebular shells. They have narrow kinematical components. Well, here we can see there that these have very narrow components. The full width maximum of these features is very small, And they typically have low excitation, and in some cases, they look like jets. This is a case of M1-66 that Jackie has been analyzing using a script that Salvador helped us to develop for this task. So sometimes they look like jets. In some other cases, they look like multiple outflows or precessing outflows or outflows moving at different directions. So there is really a large variety of the properties of these flows. And in this case, we always talk about possible precessing jets. So there is a launch of some collimation, and this is varying with time. What's the origin of these outflows? Well, there is a wealth of literature about this. Magnetic field collimation has always been thought, but actually there is very little evidence of magnetic fields with the strength at the end of the AGB phase to be able to collimate outflows in a planetary nebula. So we don't have here the mega Gauss or even the kilo Gauss magnetic fields that we are going to be needed in order to collimate those according to the models that we have on this, the simulation that we have. So then there have been also some proposals of some hydrodynamical collimation, kind of some oblique shocks that we are going to collimate the outflows. And this is one of the examples that have been claimed as a possible collimation. So we see here, you see the main shell, and the main shell is going to be ended with some like a conical shape, and the outflows seem to be protruding from this there. This is the outflow. So some people thought that maybe at some moment the fast stellar wind from the central star is going to be somehow collimated through different shocks, and at the end produces this outflow. Models, hydrodynamical models have been developed, but actually it seems that these kind of processes are quite unstable. So this is something that was proposed at some moment, but it's not really in the mind of researchers right now. And finally, maybe the most successful theory about this is the possibility that at some moment in the evolution, in the late evolution of the central star of the PM, there is the development of some interaction with a binary companion, and this is going to produce a accretion disk, most likely on the companion, which is going to be accreting mass from the AGB, from the heavy AGB wind, and this is going to be able to produce an accretion disk and some collimation of outflows there, probably going through a common envelope phase. Outflows, they have a large variety of properties besides the low excitation and the collimation that we see, and so there has been also many naming conventions for these outflows. Some people developed the idea of flyers, the fast, low ionization emission regions, back in the 80s. Jose Alberto Lopez developed the idea of BREDs, bipolar rotating episodic jets, so we are launching jets at different directions, and this is going to be interacting with the nebular shell. Most likely, probably the last compilation of properties of these outflows was developed by Denise Gonçalves in 2001, where she put together all the low ionization structures of planetary nebula. Sometimes we have some features in planetary nebula that have low excitation, but they don't really have significant variation with respect to the velocity of the main nebula. There is another thing here I'm going to point out here. This is the cat's eye, and we see here one of the typical examples where we may have like two different outflows going along different directions, and you see that there is the development of some bow shocks there. So I'm going to emphasize this in the next slide. this is kind of the same image that has been heavily processed, and now we see all those kind of ring-like and arcs structures around the AGB, around the star. Those are supposed to be kind of the last gasps in the mass loss from the AGB phase. And one thing that you see here is that until very recently in the history of the star, the mass loss had a spherical symmetry. Basically, the mass loss was symmetric. But in the very last process, in the very last formation of the PN, something changed. So jets started to go along different directions, and we have now kind of elliptical main shells and two conjoined bubbles there. So at some moment, very late in the evolution of the PN, something changed from the spherical symmetry of the AGB wind. And those processes where jets or collimated outflows were involved, they really have a very active role in the formation and the shaping of the planetary nebula. So the idea today that introduced Rahavendra Sahai and Trager in 1998 is that many of the asymmetries that we see in planetary nebula, they are due to the action of late outflows in the late AGB or early post-AGB phases of the formation of the PN. So let's go back to the topic we want to develop here. We see an outflow, we see something that has low ionization. We can determine the position on the sky, the distance to the central star. We can measure the radial velocity. We can determine what's the velocity with respect to the system, so the systemic velocity, and from there we can determine what's the expansion velocity. But because we don't know the orientation of the outflow, we don't know what's the angle with the line of sight, then we cannot determine what's the real distance of the outflow to the central star, and we cannot determine neither what's the real expansion velocity. So here there are two examples with different angles, and so for the same radial velocity that we are measuring there, we have very different space velocity. So this is basically, it's undetermined from the observation. And also the distance, the real distance of the outflow to the central star, it's also varies significantly for different orientations. So basically we know the projected distance to the central star, we know the radial velocity, so the velocity along the line of sight, but we don't know the real distance of the outflow to the central star, neither the real velocity. And we don't know neither the real age of those outflows. Sometimes we are lucky and we can determine this. Maybe we know that this is an elliptical or bipolar PN, and we can determine the orientation using spatiokinematical models, and then we assume that the outflow is going to have the same orientation, the same inclination with the line of sight as the nebula. So this way we can determine its true velocity. In some other cases, there is an ensemble of features there, like in this PN. This is NGC 6884. Back in the 90s, Luis Miranda, Chema Torres, and we realized that they have different velocities that we can fit using this model. So kind of an spiral which is going through a conical structure. And in this way we can determine what's the true velocity and what's the inclination of the outflow. But those are very, very few cases. The width of the line at certain intensity has also been suggested to be an indicative of the true velocity. But it's really very difficult to measure that velocity. It depends on the depth of the observation, and probably it's very dependent on the conditions of the observation. So we try to apply a statistical approach. So let's imagine that you have one outflow, moving at some speed For instance, this one. Oh, sorry. This one, you have one single outflow, and this is moving at this speed. So we made all the mathematics, and then we derived what's the probability of detecting this outflow at different speeds. So this is going to depend on the inclination angle of the outflow. And then it happens to be something like this. So this is really, when you have one outflow that moves, let's say, at 60 kilometers per second, then the probability to detect this outflow at a velocity between 0 and 60 is the same for all velocities. And this is just because of the geometry of the problem. Of course, we don't expect to have a distribution of collimated outflows which is just a single value. We may have a different kind of distribution. We try here, for instance, one which is like a square or a Gaussian distribution, and then we obtain distribution that have something like this. So this is the distribution of the space velocities, and this is the distribution of the observed radial velocities. For instance, if we have something like this, like two different components, either Gaussian or box shape, then we have this other distribution. So we have the mathematical tools to apply to a sample of collimated outflows. Then we needed this sample, and this is something that Jack is going to tell you how we obtain this.
The sample compilation for this statistical work. And, now we select 57 planetary nebulae, and most of them have 2 or 3 collimated outflows. For that reason, in total, we have 89 collimated outflows considered in this statistical work. And from the literature, we compile the kinematical information. So, no lo sé usar. Well, in this part, we have the kinematical information for planetary nebulae. We have the distance, and we measure the semi-axis, semi-minor and semi-major axis using the HST with high technology, using a HST image, and the expansion velocity of the planetary nebulae while compiled using the literature. And from the collimated outflow, the kinematical information were compiled to the literature, and we have the radial velocity and 2 more parameters: the angular size, that it is theta is, and the relative size, that it is as letter x. And we have this table now. So the angular size we measure using HST image. This is, for example, for this planetary nebulae. And we have the theta is the radial distance to the tip of the collimated outflows and to the central stars. And the other parameter is theta pn outflow, that is the radius of the nebular shell. And we consider at the 2% level from the peak intensity. And other parameter is the linear size, that it is this parameter times the heliocentric distance. And this parameter, that this is the relative size, is the ratio between this parameter and this other one. And this is very important because tell us where is the collimated outflow in the nebula. Other thing that I need to tell you is that we only consider in this statistical work planetary nebulae. I mean, protoplanetary nebulae is not considered here. Why? Well, because there are different reasons. The first is that the angular size are difficult to assign in protoplanetary nebulae. Other thing is that the expansion velocity is very difficult to measure in this kind of object. And some of planetary nebulae do not show H-alpha emission. For that reason, we don't consider protoplanetary nebulae in this work. Well, after we compiled all this kinematical information, we plot the radial velocity in the y-axis and the relative size in this axis. So, for this figure, we have the radial velocity 2 and the linear axis here. This is RS, sorry. So we observe that most of collimated outflow is in this box. So this is a zoom of this region, and you observe that collimated outflow have a radial velocity lower than 100 km per second. This is more clearly in this distribution. So the most collimated outflows is here, and few collimated outflows are moving at high velocity. And the other thing is that this parameter, if we observe, we have a lack of data in this point. I mean, all the collimated outflow is in this zone. They are less to 0.5 parsec. For this figure, is more clearly that in this zone, we have a lack of data points. And, well, can be for different reasons. I'm going to tell you in the follow slide. Okay, we have in this histogram, you can observe that this parameter, that this is the relative size to the angular size, plot with the total of number of outflows. We observe that a significant fraction of outflows is in this zone with x equals to 1. What means that if this parameter x is equal to 1, means that the outflow is in the edge of the nebula. If this parameter is low than 1, is that the outflow is outside of the nebula, inside of the nebula. And if this parameter is lower, the outflow is outside of the nebula. And this is more clearly in this planetary nebulae. So in this part, we have this node here, and this is the radius of the planetary nebulae. So the collimated outflows is in the edge of the nebula. But in this case, is a little different. We have two collimated outflows, here and here, and this is outside of the nebula. But if you observe deeply, we have other collimated outflows here, and this is in the edge of the nebula. So these parameters is approximately 1. Despite of outflows is founded inside or in the edge of the nebula, we are able to detect them. And there are other planetary nebula that have collimated outflow, but in an image is not detectable. So we need to use the spectroscopic observation. This planetary nebulae we call a spectroscopic bipolar nebula. And also, one of bias that we don't detect collimated outflow in this part is maybe because the outflow is directly pointed in the line of sight of the observer. And other planetary nebulae that we don't observe in this part is because they are fast and maybe they are old. And maybe, well, the thing is that the image of the planetary nebulae only cover the principal nebula. And maybe if the collimated outflow is very old, maybe these outflow far away of the nebula, and we don't detect them. And for that reason, maybe we don't detect planetary nebulae in this part, and this part, and this. And well, we have some results. You have more technology.
Now that we see the distribution of the outflows and the velocity here, then you probably know why I made different guesses as for the how to obtain the observed distribution of radial velocities with different distribution of space velocities. And so you can see that there is a main component here reaching up to 100 kilometers per second, and then there are just a few then at high velocities. So you see that we definitely need to have at least two different components of the space velocity. So when we make the numbers, this is the same plot that we have before, but using a chi-square statistic approach. So we make a statistical fit, and what we obtain is that the best distribution of the space velocity of the flow is something like this, with two Gaussian components. So there is one main component with it has about 85% of the outflows. So most of the outflows, they move there, and they have a mean velocity of 64 kilometers per second. This is just a few times, maybe up to 3 times faster than the RPN. So this is the distribution of the velocity of the PNE. It has an average of 22 kilometers per second. I mean, of those PNE. And then there is one second component, which is less frequent. We cannot really say exactly what's the velocity of this outflow, neither the width, but probably something with a mean velocity of about 180 or 200 kilometers per second. And with this width is going to be able to cover the properties of the observed distribution. So the space velocity of the collimated outflows in PN is bimodal. And we can also do the same for the distribution, the observed distribution of the projected sizes, or the projected distances to the central star. So this is the observed distribution, and if we apply the same mathematical method, then from this single distribution of size, we'll get something like this. So we can make the same application to different distribution, and similarly, we have like one main component here, a secondary component there. So this is going to tell us that probably we have also a bimodal distribution of the radius of those outflows. And when we make the numbers, we get also to this conclusion. So we have about 70% of the outflows, they have a radius and a size, which is an average value of 0.13 parsecs. And there is a second component, which is 30%, which a size of 0.4 parsecs. Again, if we compare those sizes with those of the RPNE, we have that this is something like about 2 times larger than the RPN, that has an average radius of 0.74 parsec. So maybe we can think that there's a bimodal distribution there, and so it may have implication as for how jets are formed, different mechanism, interaction with the nebular envelope. But before we go into this, we need to look into detail to those outflows. And this is something that Jackie has made.
Well, as Martin told us, there is a bimodal distribution in the velocities of outflows. But first, I'm going to talk about the new sample that complete the statistical work. And this is a 12 planetary nebulae. So we have a high quality narrow band image obtained by the HST or the Nordical Optical Telescope, or BLT, in different bands: nitrogen, H alpha, oxygen, And also we have a high dispersion spectra with different, obtained with different telescope and with different spectrograph. So these spectra were obtained, place the slit in different position and angle. And we have this column, and this positional angle depends of where is the collimated outflow in the planetary nebulae. So after a study of this kinematical planetary nebulae, we found 3 types of structures. The type 1 is jet-like collimated outflows. We have 2 examples for this kind of outflows. This is the jet-like here, and in a position velocity maps, this is nitrogen, we have the jet-like in this part. Also, in other planetary nebulae, that is M240, we have this jet-like here, and this is also detected in the position velocity maps or PV maps. The type 2 that we found of this sample is multiple or precessing collimated outflows. This is for this nebula NGC 6210. And if you observe this slit, that this is at 156 the position angle, you have this collimated outflow here, that this is labeled as C. And you observe this faint material here, and its cold part is here. So this is represent like a S shape. And this kind of morphology is associated like a precessing outflows. Well, in the PV maps, you observe the collimated outflow in this part. And other example is M31, and we observe the same thing. You can observe this collimated outflow here and here, and the S shape in this part and in the other part. This is shown with this blue arrow here. Again, this is an X shape too, and this is associated with a precessing outflow. And in the position velocity diagram, we have the collimated outflow that is correspond with this. And also, we are able of obtain the kinematical information of this arm that correspond to this part. So we have a three-dimensional kinematical information for this object. And maybe in the future we are doing a model to study these objects more detailed. And the type 3 is a set of planetary nebulae that have particular features. We observe this kind of material with a V shape, and you can observe in this part and in this part. And also there are other planetary nebulae that have bow shocks that you can observe in this part, here and here. And we are proposed that this kind of feature is the result of the interaction with collimated outflows with the nebular shell. And also in these PV maps, you can observe this knot and this collimated outflow here and here. And this is like an idea that collimated outflows are change the morphology. For that reason, the final morphology of planetary nebulae are distortionate. So, basically, with this new sample, we found 2 types of collimated outflows. True collimated outflows, like this, or precessing collimated outflows. and other features like bow shock, V-shape, or low ionization shock, that they are not collimated outflows. This is the result of the interaction. And we have now a table where we compiled all this information, and we describe the morphology for each planetary nebulae, and we measure the radial velocity and the expansion velocity using our spectrum. And it's important to say that we need to reassessment of the definition of collimated outflow, because now it's not clear. And well, there are different interpretations, and Martin told us.
Okay, so now we have much idea of what we are really observing. Is not just a statistical table and statistical results, but we have an in-depth image of what we are seeing. So the first thing that we see is that there is a significant fraction of sources where we have the collimated outflow just at the edge of the PM. There is also a number of collimated outflows whose expansion velocity is about the same or even smaller than the expansion velocities of their PN. So in those cases, we have seen that the effects of those outflows are really noticeable in the morphology. So we have this V-shaped or those bow shocks there. So we propose that there is indeed a population of outflows that are still embedded within the nebular shell. So they have not been able to break through the nebular shell, and they have been trapped inside. So I can show here you an example. So this is the case of M1-66. So we have this V shape there, and then the outflow is able to break through, pierce through the nebular shell, and you see it outside. So this would be one case where the momentum of the outflow is large enough to escape from the nebula. And then we have this other case where we see this V shape, but then there is no outflow outside. So there is our idea is that those may be like light outflows, so those are outflows whose density is smaller than the density of the AGB wind. So they push, they press the material, they sweep it up and produce this kind of concentration of material at the edge of the nebula, but we don't see the outflow. The outflow is, at least from the optical observation, is not visible. So that would be one kind of outflow. And then also we see that there are very really a small number of outflows that they have large velocities. Some of them they have seen at distances much larger than the PN, like this Fleming one, where you see this outflow moving up to there. And so we consider those maybe, we interpret that those may be the results of heavy outflow. So those are like bullets, large density bullets that they just go through the nebular envelope and escape from the AGB wind. So this will be the progeny of those that we see in some proto-PNE, like these two, or the water fountains, where we see very highly fast outflows that probably they are going to escape from the nebula, and we are going to find this very far away from the nebula. In some of those cases, those have been associated with binary central stars. So they may be revealing the interaction, the collimation through accretion disk. Then there is another thing that we see that the space velocity and distance, they are both bimodal. But they are not independent. They are tied one to the other. And also they are going to depend on what's the age of the PNE, what's the age of the collimated outflows, what's the time span, so the duration of the outflows. And this is an interplay that we can try to resolve. So the first thing that we see is that what are the dynamical ages of the PN that they show collimated outflows. So this is illustrated here in this histogram, and we see that typically the dynamical ages of those sources has an average of about 3,000 years. But dynamical ages are not very reliable because there are many dynamical effects. We can better look at the distribution of the sizes, and if we run hydrodynamical simulation, we see that planetary nebulae with those sizes, they have typical ages in the range from 1,000 to 3,000 years. So we only see collimated outflows mostly in sources that they are young. Here, we don't have sources younger or much younger than 1,000 years because we are excluding from our sample protoplanetary nebulae. Then we have run some Monte Carlo simulation adopting the distribution of space velocities that we have derived and trying to fit the distribution of the radial sizes of those outflows. So here is in red the observed distribution, and in black is the synthetic distribution. So where T min and T max is the minimum age of the outflow and the maximum age, and so the duration is going to be the subtraction of these two. So we can see that there are some cases, let's take this one, where basically they don't match. I mean, if planetary nebula, if the outflows have an age at least 2,500 years and are at least older than 5,000 years, there is no way we can match the observed distribution of outflows with that we see. We can go to the other side of the panel. So let's say here, and we see that if the outflows are too young and their duration is too small, we can neither fit the distribution that we observe, which is the red one here. So we have made a selection of what are the best cases, and we see that outflows, they have a minimum age between 500 and 1,500 years, and they have a duration between 1,500 years and 3,000 years. So this is indicating that planetary nebulae are mostly coeval with their jets. So PN and jets, they were produced at about the same time. And also that the outflow duration is smaller than 3,000 years. So they disperse in a time like this. So these are our conclusions. So in these two studies that we are presenting, we see that the space velocity, the true space velocity, independent of orientation of the collimated outflows, is bimodal. Most outflows, they have velocities which are just 2 or 3 times the expansion velocities of the planetary nebulae. For many of those, we propose that they are embedded within the nebula. They have interacted, they have produced some effects, they left some imprint in the AGB envelope, and then they just propagate with the nebula shell. There are very few collimated outflows with high velocities that we can really call jets, and we propose that they proceed from dense knots of material that they just go through the nebula without too much interaction. So we have been able to determine the timing of collimated outflows and their PN. Collimated outflows and PN, they are coeval, and we only see those in young planetary nebula because outflows, they disperse in very short time scales. And finally, we are talking here about collimated outflows, but we probably need to think about a real definition. I know there is many names in the literature. Basically, every single author has its own name, but we need to split out what are jets, what are outflows that they produce some effects in the nebula shell, and what are some outflows that we don't see, but we see their effects on the shell. Thank you very much.
Thank you, Martins. Thank you, Jacqueline, for this very nice dual presentation. The talk is open for questions. Isabel.
Very nice talk, and I will see my comments on the Pimpinella later on, which is you've said that you have a spectroscopic data, right? But it is long slit, right? So is there any way of constraining, better constraining the the true velocities that you have in case you have a distribution, an IFU data that you can compare with a model or somewhat like that.
But remember that you need to have a relatively high dispersion, at least, let's say, 20,000, and you already have one instrument in mind. And you also need to have a field of view which is large enough to cover the piano. So in some of those cases here, let me see. Okay. So we cannot see here. Here, you see that this has a very small size, something like this, and this could be a very suitable target for Megara using the high dispersion grading on the H alpha and nitrogen 2 line. So indeed, Jackie, who has been the person who coined the name for spectroscopic bipolar nebula, has a project to use Megara for some of those targets. So we have already identified, using some NOD and HST observation, very good candidates that they are suspected to have collimated outflows, but where you really need to have something like Megara observation to cover the whole field of view and then determine the expansion at different locations.
And you high resolution. High resolution like long slit, so this is very comparable.
Then there is another question that I'd like to emphasize here. You go to one telescope and you get the image. Then you go to another telescope and you get the spectra, high dispersion spectra. So the condition of the observation here and there, they are not the same. And so at the end you have maybe the slit is not going exactly through the place where you thought it was going. So sometimes interpreting images and high dispersion spectroscopy obtained at different sites is very difficult. So if you have IFU where images and spectra are obtained at the same place with the same observing condition, that's the best way. Yes.
I guess I had a couple of questions. For those outflows still embedded in a shell, it could be interesting to detect it through radiomolecular observation carried out with interferometers or single dish observations. I don't know if you had considered or you had checked in the literature some molecular counterparts for these optical outflows, I mean CO or other tracers.
There are very good examples in the literature about this. I'm thinking about NGC 1727, where Gerd Cox found some molecular outflows there. Sometimes you find those through H2 observation, sometimes you have to go to interferometric observation with CO. And then you are able to see how the shell is being distorted, but you see nothing in the optical, and then you realize that you have some molecular outflow running out there. CRL objects like this, or CRL 618, you find those outflows in molecular observation, and they are really in a very early phase of the collimation, which is very important, and also in the very early phase of its interaction with the nebular envelope.
So I think it's about, if you go further, the next image, like in HGC 6020.
Which one?
HGC 6020 with the 4 images are.
Yeah.
Like that, if those low ionization clumps in the left one, sorry, you don't see any molecular emission because it's already ionized inside those. But in very young ones, you can see a torus, and that's what Martin is talking about. But I think you were asking about the clumps inside it. Or yeah, you don't see any molecular inside it.
But you see those on protopian, But then you also may see those in some PN, like 1727, because the evolution of the star is so fast, and clumps are probably so dense that they have still the chance to survive in these conditions.
For both. Sorry I was late, and I don't know, how do you transform radial velocity to true space velocity? I think that it is a geometric question, it is a statistical approach of that is something, point by point projection.
We are very proud of this figure, so we don't mind to repeat the explanation. So in this column, I have the distribution of real space velocity. So this is just a model. Imagine that you have outflows, all your outflows are moving at the same speed, 60 kilometers per second. Then they are going to be oriented along different directions. The ones that they are pointing at you, that you are going to see with 60 kilometers per second, are very few, just because they need to be pointing. The ones that they are on the plane of the sky, almost they are a lot, because you have all the circle there. You have many azimuthal angles there for this. If you make the numbers, if you make the interval, and then you assume that the orientations are random and that you can detect all outflows independently of the orientation, then you are going to have a distribution like this. So it's equally probable to have an outflow with velocity going from 0 up to its real velocity. Then it's a statistical approach. And then we have a sample of almost 90 collimated outflows, and then we apply those models to the sample. We apply a chi-square best fit, reduced chi-square, and so what we get at the very end was this distribution. Oh, sorry, this is for the space.
The velocity.
And this is for the velocities. So this distribution of the space velocity is the one that best reproduces the distribution of observed radial velocities. And this is from a statistical point of view. I cannot tell you what's the velocity of this outflow, but I can tell you what's the distribution of the velocities.
Any other question? Pepe.
Thank you. Very nice talk. I'm sorry I was late too, but I was wondering whether you mentioned maybe at the beginning of the talk that whether the classical type 2, type 1 planetary nebula classification makes sense for these conclusions. Are they related, or are any, classification issue behind, or this is just statistical approach?
Yes,
The paper. But this corresponds to, well, I remember that the type 1 and type 2 is related to the velocities. If the radial velocity is less to 60 kilometers per second, they are type 1, and they are related to the abundance with nitrogen and helium.
Yeah, one may collimated outflow, there is an evolution through a common envelope, and this is going to change the chemical composition of the source. But to my recall, there has been some trials to look at some trends in the distribution of sources that they have collimated outflows. Denise Gonsalves made some study, Romano Corradi too, and they find that there is not a clear correlation between, for instance, the location, the scale height on the galactic plane of these sources. If you look at bipolars, they tend to be closer to the galactic plane than round or of elliptical. But when you look at sources that they have outflow, there is not such a clear correlation. They seem to be somewhere in between. So
it doesn't seem that more massive progenitors are going to produce collimated outflows. And that could be reasonable. I mean, that would be what I would expect if collimated outflows are produced not by the central star, but by its interaction with a companion. So this is going to be independent on the mass of the central star.
Any other question? If not, thank you again to both speakers.